Good evening. Today's goal is to sketch polynomials using their roots. Roots, of course, are just x-intercepts and their end behavior. By end behavior, we just mean, is the function going to look like this, like a parabola that's concave up or concave down, or is the function going to look more cubic? Okay, let's take a look at example 1. Express f of x equals x cubed minus 7x squared plus 32x minus 60 in fully factored form. Fully factored form means we want to factor all the ways such that each factor is linear. Given that f of 3 equals 0, there's our clue, and we're going to sketch. So we've got two goals here. Okay, f of 3 is 0 is our clue that we know 3 is one of the roots, so we can use synthetic division to divide the polynomial. Indeed, we can see 3 is one of the roots. We get a remainder of 0. So f of x is equal to x minus 3. If 3 is a root, it has the factor x minus 3 times x squared minus 4x plus 20. Now let's see, this is quadratic, what's left over, this factor, which means we haven't fully factored the function. Not all of our factors yet are linear. So let's see if we can factor x squared minus 4x plus 20. 2 times 10 won't work, 4 times 5 won't work. Yikes. Well, because x squared minus 4x plus 20 can't be factored, we can use the quadratic formula. In order to figure out what those last two roots are. We know by the fundamental theorem of algebra that this cubic function, of course, has 3 roots. We know one of the roots is 3. We just have to find that other one. So we have the square root of negative 64 all over 2, which is 2 plus or minus 4i. So in fully factored form, our function is f of x equals x minus 3 times x minus 2 plus 4i times x minus 2 minus 4i. If a is a root, x minus a is the factor. Okay, so there's our fully factored form. This is in all of the factors are linear because they all have a power of 1 on the x's. And now we're ready to actually graph the function. We know it's a cubic function, so it'll have this shape, especially since that positive leading coefficient is 1. We know the function has a root at 3, and the only other roots are imaginary, so they won't actually touch the x-axis. So we can leave our function like this. Okay, let's take a look at the next question. We're going to sketch 3 different functions, and when I look at these functions, I see that they look really similar. For example, f and g are both going to have roots at 0, and they're both going to have roots at 3. I can tell that just because the functions are already factored. But what I notice is different about these functions is where this exponent lands. So let's take a look at the table of values to see if we can explore what effect the 2 has on the graphs of the function. So when I'm looking at the table of values for f, these y values are negative, then we've got a root at the origin. We knew that because of the factor x. Then I can see that the y values are positive. Then I've got a root at 3. Again, we knew that because of the factor x minus 3. And then, this is interesting, these y values are actually positive again. So what's happening is that the function is bouncing off of the x-axis, let's see, at the y value 3. So f is going to look like this. Whereas g looks a little bit different. Here we go. G has negative y values, then it's got the same roots, but g has negative y values again after the root at 0. So g is going to functionally bounce off of the x-axis at the root 0 and then cross through the x-axis at the root 3. This is because of multiplicities. The multiplicity of a factor is the number of times that that factor here we go. The multiplicity of a factor is the number of times that factor appears in a function. So f of x is the same thing as saying 5x times x minus 3 times x minus 3. the factor x minus 3 occurs twice. So the factor x minus 3 has multiplicity 2. That's why we see the function bouncing off the x-axis at x equals 3. Anytime a factor has an even multiplicity, the function will bounce off of the root corresponding to that factor. That's why we see g is bouncing off of x. G of x is the same thing as 5 times x, x is the same thing as x minus 0, times x, again x minus 0 times x minus 3. This time g has the factor x minus 0 2 times. We would say the factor x minus z has multiplicity 2, and that's why the function bounces off of 0. But g only has the factor x minus 3 1 time. That's why g just slices right through the x-axis at 3. So let's take a look at h. H also has roots at 0 and 3, but h is going to be a degree 6 function, right? If we multiply all these factors out, h is the same thing as negative 5 times x minus 0 times x minus 0. That factor has multiplicity 2 times x minus 3 to the 4th. This factor has multiplicity 4. And so if it's a degree 6 function with a negative leading coefficient, we know it'll look like this. So let me just map that end behavior in there. And we know that this factor has multiplicity 2. We're going to bounce off of 0. And this factor has multiplicity 4, so we're also going to bounce off of 3. One more example today. Name all the zeros of this function and sketch the function given that f of x has a repeated root at negative 4. A repeated root at negative 4, there's my first clue. So I'm going to use synthetic division twice, maybe even more times, with negative 4. Let's see, negative 4 times negative 31 is 124, plus negative 152 is negative 28, times negative 4, you guessed it, is 112. And because they said it's a repeated root, I'm going to do synthetic division again with the same value. Is equal to x minus 4, I'm sorry, x plus 4, because of this synthetic division, times x plus 4, because again we were able to divide using negative 4 as a root, times our leftover. So x squared minus 6x minus 7. Lucky for us, this factors nicely. I'm just going to wind these two up. This is the same thing as x plus 4 squared. I'm going to factor x squared minus 6x minus 7 into x minus 7 times x plus 1. Now I'm trying to name all the zeros and sketch the function. So I can see the zeros here. I can either write that the zeros of the function are negative 4, 7, and negative 1, or you could say negative 4, which has a multiplicity 2. Oops, sorry. Multiplicity 2. 7 and negative 1. This way, you can box them either way. We can see that you're accounting for all 4 zeros since the function is degree 4. And the other thing we want to do is sketch it. I know that this is a degree 4 function with a positive leading coefficient, so it's going to have sort of this parabolic shape, concave up. I know that there are roots at negative 4, at positive 7, and negative 1. So let me just go ahead and plot the end behavior of it. Now I can plot the middle. I know that at negative 4 I'm going to bounce off the function since there's a repeated root of even multiplicity. Then I need to slice through that negative 1 and slice through the 7 because x plus 1 and x minus 7 only have an odd multiplicity of 1. So here's my sketch.